next thing we're going to discuss are tilings. Now, first we'll define a tiling. A tiling is a covering of the plane, so the two-dimensional plane, two-dimensional space, the Cartesian plane you can think of. But a tiling is a covering of the plane by non-overlapping regions, which we call tiles. They can't overlap. So a tiling just covers the plane without overlapping. And we're going to talk about certain kinds of tilings depending on which shapes we're using. But the next definition, well, we'll see in a moment. A tiling is edge to edge if for each tile, each edge coincides with an entire edge of a bordering tile. So what does that mean? Well, that's a lot of words, but let's illustrate using this example what we mean by an edge to, well, using these two examples, what edge to edge means. So example, the following is a tiling using a rectangle. So here our tiles are going to be a single rectangle. The tilings we consider will be using one shape. So you could do tilings with multiple shapes. We'll just stick with one shape for here, because that's illustrative enough. So the following is a tiling using a rectangle. Well, for rectangles, I like to, you could just draw out a bunch of rectangles that fill in space, but I like to first break our two-dimensional space into strips like this, and then they can continue on in either direction. And then we can fill in each strip with rectangles. So we're going to use one rectangle, and we're going to put the rectangle there, and these are all going to be the same rectangle. Keep going in that direction, keep going in that direction. And then you do the same thing down here. You can go like this. All of these are the same rectangle. And similarly down here, you can keep going with the same rectangle, and then you can keep going up, and you can keep going down. So right here we have an example where we filled in all of two-dimensional space with a single rectangle. Well, with multiple copies of a single rectangle. But notice here, this tiling is not edge to edge, because what's the definition? If for each tile, each edge coincides with an entire edge of a bordering tile. Well, take this tile up here. These two side edges, the vertical edges, do coincide with an entire edge of a bordering tile. But the top and the bottom edges don't. Well, the top, if we continue this same pattern, it won't. But the bottom definitely doesn't, because the bottom hits this rectangle over here and this rectangle over here. So this is not edge to edge. But it is still a tiling. And this next example, we'll do an edge-to-edge tiling. So the following is an edge-to-edge tiling using a rectangle. Well, again, I'm going to break down two-dimensional space into these strips. And then we're going to put a rectangle here, put a rectangle there, put a rectangle there, keep going, and then just put in the next strip underneath it the rectangle immediately under that one. And similarly here, and so on, and then you keep doing that. Keep going up, and you keep going down. So this right here is edge to edge. Now, right here we have tiling using rectangles. We're going to talk a little more about tilings using general quadrilaterals in a moment. But first, I'd like to cover regular tilings. So first, let's define what I mean by a regular tiling. Definition. A regular tiling is an edge-to-edge tiling which uses only a regular polygon as its tiles. So a regular tiling is edge to edge, and it uses only a regular polygon. A rectangle is not a regular polygon. So we'll look at a couple different regular tiling. Well, actually, we'll look at every regular tiling that exists. But it uses only a single regular polygon as its tiles. You can see from this example that we can find a regular tiling using squares if we just say that these rectangles are squares. But are there others? Theorem. The only regular tilings use regular tilings use and then we have I'll do bullets. One. I'll tell you there are 3 regular tilings. Well, we've already seen one here with squares, if we say all those rectangles are squares. Squares, I'll put in the second bullet point. Squares are regular 4-gons. What about regular 3-gons? Regular 3-gons, what would that look like? Well, a regular 3-gon is an equilateral triangle. A triangle where all sides are the same and all angles are the same. Can we use them to fill in an edge-to-edge way, 2-dimensional space? Well, let's try. Let's try taking these 2 strips. Well, let's put a triangle somewhere. How about right there? There's an equilateral triangle. Well, let's try to fill in the rest of this horizontal strip. Remember, it needs to be edge to edge. So what we can do is put the second one right there, where they meet at this edge. And so we kind of flip it upside down. And then we keep doing that as we go over. You keep doing that, and you keep doing that also in this direction. Well, that's great. We filled in a strip in an edge-to-edge way. Can we extend that to the next one down? Because if we can do that, then we'll get everything. Well, notice first you can't do that, because now it's not edge-to-edge. We need it to be edge-to-edge. So what can we do? Well, we have this edge. We can make that one of those edges, which would make the other 2 look like that. So right here, that is edge to edge, and then we just keep going on in the same way as before. Keep going up, keep going down, and right here we have filled in 2-dimensional space using equilateral triangles. Equilateral triangles. God, I'm having trouble spelling words properly. Triangles, that's not a complicated word. T-R-I. So this theorem, the only regular tilings used, it could have just said triangles, but I'll emphasize that they're equilateral by saying equilateral. What else? Well, we saw using squares what that would look like. So this is, I mean, you could just adjust the previous example and say it's squares. So right there, that's what a tiling using squares would look like. What about next? Well, the only regular tilings, there are 3 of them, And we will explain why there are only 3 of them. But before explaining why the ones that don't exist, let's explain why the third one does exist. There will not be a tiling for irregular pentagons, but there will be a tiling for regular hexagons. Well, how can we do that? You may actually be able to see how we can start doing it if you extend out that equilateral triangle argument. But the way we will start this is not by dividing two-dimensional space into strips. What we'll do is I'll take that regular hexagon that's drawn right there. Maybe I shouldn't, so it parallels that. Yeah, I will. There's not much room on the board. Take that regular hexagon, and what we're going to do is just put another hexagon next to it, like this. Great, there's another regular hexagon. And what we're going to do is see if we can fill this piece in with another regular hexagon. But to do that, we need to know how much space is left there. And we also need to know how much space a regular hexagon takes up. Well, I will tell you now, and I'll tell you why in a moment, all of the angles inside a regular hexagon are 120 degrees. If they're all 120 degrees, well, what is this remaining gap? This remaining gap is another 120 degrees, because an entire circle is 360. So we have this 120, this 120. What's left is 120. And inside that space, we can fit another regular hexagon. And that keeps going. 120 here, 120 here, so there's another 120 left. And in there, you can fit a regular hexagon, even though that drawing doesn't really look like it. Similarly over here, the same thing applies. You can fit a regular hexagon in there, and this keeps going. So you can get a tiling using regular hexagons, an edge-to-edge tiling using regular hexagons. So right here, we have the 3 regular tilings. What about the other shapes? So, in other words, why only these 3? Well, to explain this, we're going to first recall something from geometry. The interior angle of maybe I should say an interior angle. An interior angle of a regular polygon is given, the measure of an interior angle, that's okay, is given by 180 times n minus 2 over n. And you can see with the regular hexagons, if you let n equal 6, you get 180 times 4 all over 6. 2/3 of 180 is 120. But so what happens if we try to do a tiling using regular pentagons? Well, what do they look like? They look like this. In all angles, what do all angles measure? 180 times 3 over 5. 180 divided by 5 is 36, because 180 times 2 is 360. 36 times 3 is 108. So all of these angles are going to measure 108. So let's try piecing together pentagons. There's a second pentagon. There's another 108. Do we have room for another pentagon? Well, yes, we do, because the remaining angle in here is 144. So we can fit another pentagon, but notice what we get. Let's see, what would it look like? Something like that it would look like, with 108. But what is left in this gap? Can we fit another pentagon? We can't fit another pentagon. Because what's in there is 36 degrees. These add to 324. 324 from the full circle gives us 36 degrees. So notice there's a 36 degree gap. And we'll never be able to fill in that gap using one of these pentagons. So notice there's a 36 degree gap, and a pentagon, a regular pentagon that we're using, won't fit. And because of that, we're never going to be able to tile the entire plane using regular pentagons. What about regular 7-gons? Heptagons. Well, let's see if I can draw one of those. 1, 2, 3, 4, 5, 6, 7. Yeah, that's okay. What is the angle? Pretend that's regular. What is the angle of a regular 7-gon? Well, it doesn't simplify to a nice number, which might tell you right away that it's not going to add to 360 like hexagons did. But I will tell you it's about 126.5 degrees. Something like that. Is it? It's 126. Isn't it? Actually, I'll just find it exactly. Where's my phone? I don't have my phone. I was mistaken. It's 128.5 degrees about. It's about 128.5 degrees. And what happens when we try to fit two of these together? Well, we have this 128. Let's just say 128. And what if we put another one next to it? Well, it would look like that, with another 128. And what's left? This remaining piece, so if this is 128, we'll just assume 128 there. 128 and 128 make 256, so what's left is 104 degrees. If that's 104 degrees, a regular heptagon won't fit, because that's only 124 degrees, and a heptagon needs 128.5 degrees. What about octagons? Well, regular octagons are much easier to draw than regular heptagons. There's a regular octagon. The angle inside measures to be 3/4 of 180, which is 135. Because 180 divided by 4 is 45. 45 times 3 is 35. 135. Well, let's put another octagon here. We have another 135, and what's left here is a 90-degree wedge and another octagon won't fit. And the argument for 9 gons. Maybe I should have said 8 gons since I wrote 5 and 7 gons. The argument for 9 gons, 10 gons, and so on, any finite number of gons larger than or equal to 7, this same argument will hold, because the angle on the inside is going to be a little less than 180. You put 2 together, and you can't put a third one there. Now, the pentagon is actually, I would consider, the most interesting, because you could put 3 together, but with 7 or more gons, you can only put 2 together. So I'll just say similarly for n gons with n larger than or equal to 9. And that'll be the end of our proof, because there are no 2 gons and there are no 1 gons. So we've shown every regular tiling. And there's really not much more you can say about regular tilings, so we'll move on to irregular tilings. And we won't cover every irregular tiling. There are many in the textbook, and there are many more in general. But we'll cover a few of them. Irregular tilings. Now, an irregular tiling is an edge-to-edge tiling that uses irregular polygons. So maybe I'll say that. Are edge-to-edge tilings using a non-regular polygon. And we'll look at several of these. First, we'll look at parallelograms. We'll look at parallelograms. In parallelograms, the argument is similar to rectangles, because we can fit parallelograms within these strips nicely. There's a parallelogram. Then we'll just keep translating that parallelogram over and keep going. And then we do the same thing down here, but we can't put a parallelogram here because it needs to be edge to edge. So we need to be sure we're keeping track of our edges. Put one here, like that, and like that, and like that, and so on. And then you continue in the other direction, the up and down directions as well. Trapezoids follow a similar argument because they have one pair of parallel sides they can fit within the strips. We saw for equilateral triangles. On the homework or maybe the worksheet will be isosceles triangles. Here we'll show for scalene triangles. What's a scalene triangle? Well, all the angles, all the sides are different. So right here we have a scalene triangle. How can we do a tiling, use an edge-to-edge tiling using scalene triangles? Well, what we can do is take 2 of them and make a parallelogram. Parallelogram is a long word. We can make a parallelogram, because notice parallelograms, you can divide them into 2 triangles. But here we'll take 2 of them, so we'll take this one like this. And then we'll take the other, and I'll use a different color for that. Let's use blue. And take the other, use this same edge, but put that longer edge up here. And then the other edge like that. So right here, we took 2 and made a parallelogram, and then proceed as in 1. So now we have a parallelogram. You can fit them together in the same way. You can fit scalene. You can make a tiling using scalene triangles by doing them 2 at once when they take this form. So I just mentioned on the worksheet or the homework that there will be a tiling using isosceles triangles as well, similar to that. But notice an edge-to-edge tiling exists for, what do we notice? Well, we did scalene triangles, we will do isosceles triangles, we did equilateral triangles. So an edge-to-edge tiling exists for any triangle. Well, that's nice. An edge-to-edge tiling exists for any triangle. Does that happen for other shapes? Well, triangle is a three-gon. Does that happen for other shapes? Well, what's the next gon? How about a four-gon? What about general quadrilaterals? Well, what can we do with those? So when we were fitting together hexagons and octagons and all those, we took advantage of the fact that the hexagons perfectly added up to 360 if we put three together. Similarly, we didn't mention for the equilateral triangles or the squares, but if you put four squares together, that again makes 360 degrees. If you put 6 equilateral triangles together, that again makes 360 degrees. Maybe I should have mentioned this. So in your notes, yeah, I should have mentioned this before doing irregular tiling. So after I wrote QED down here, well, recall and remark. An alternative proof. Oh, did I use the word proof? It should have said proof right before our equilateral triangle tiling. An alternative proof of the regular tiling theorem would use the fact that the interior angle of a regular three-gon, four-gon, or a regular six-gon divides evenly into 360 degrees. So the regular three-gon interior angle is 60, 60 times 6, 360. The regular four-gon interior angle is 90, 90 times 4, 360. The interior angle of a six-gon is 120, 120 times 3 is 360. And only, so it uses the fact that the interior angle of a, I should use the word only somewhere. Well, I'll just leave it like that. So this really should have been mentioned before going into irregular tilings. I didn't mention it. But that same observation where we fit together angles so that we get 360 degrees, that same observation is going to show up for general quadrilaterals. Now, what would a general quadrilateral look like? Well, you can draw it however you want as long as it has four sides. I happen to have one right here that I made by folding paper. I'll put it, I should continue after this. So right here we have our general quadrilateral, and the way I like to do this is by marking the four corner points of this and then just piecing them together like this. And also on this I did label these angles A, B, C, and D because we're going to be keeping track of the angles and the sides. So here's a general quadrilateral. Here's A, B, C, and D. And we're going to notice, well, we're going to recall, it's more of a recollection than a notice. Recall A, these are all angles, A plus B plus C plus D equals 360 degrees. And because of that, when we do one of these tilings, we're going to want to use in each, well, let's say at each point, we're going to want all four of these angles to show up because they add to 360 degrees. So a tiling using that shape, A, B, C, D. So a tiling using this. What would it look like? Well, I'm going to do it down here. We're going to take one of our shapes. So a tiling using this. Folding up a piece of paper into this took a lot more folds than I was expecting because I have this nub at the end that I had to keep folding in so that it looked like four distinct sides. I wanted it to be four distinct sides and four distinct angles. But what would a tiling here look like? Well, remember, we're using edge-to-edge tilings. That was part of our definition of irregular tilings. So that's the first thing we're going to know. We need the edges to match up. So with this A, B, C, D, you can't do the next one, well, how should I say, if you're going to work on, so our goal is going to be to fill in a circle with all four angles. So if we're going to work on A, meaning if we're going to try to fit angle B, C, and D around A, well, you can't take side CD and go here to get angle C, because that would no longer be edge to edge. The only edge we can put on this other side of line AD is the same line AD, but notice you can't just flip it over because that would put another angle A here. So what we can do, I marked these angles for a reason. I want side AD to be down here, but I also don't want another angle A over here, so I want an angle D. This one right here is angle D. If I put that there like that, well then angle D is going to be here. And I need to just mark off the other sides. So right now, same quadrilateral, but now angle D is here. D, A, B, C. And we keep going. So right here, we have angles A and D. Next we need angle C or angle B. So right here, we need the edges to match up. So we have side AB. I'm going to flip it around so that angle A is now up here, angle B is down here. And that will give us an angle B in the place that we want. So here's angle B, that one's angle A. Which one is this? This is D, and this is C. And all that's left, notice, all we need to do is fit in angle C, and we can do that like so. Angle C will fit nicely because we have side DC, side BC. All we need to do is mark off a point down here for A, and then we have the same shape showing up. So there's angle C, angle D, angle B, and angle A, and so on. You can keep continuing this. I'll draw a couple more. So if we work down here, we have C and D. We need A and B. So here's side BC. I'm going to flip side B to C. My quadrilateral now has angle B up here, angle C down here. Mark off the corners, and then fill them in. And we have now A, B, C, D. All that's left in this piece now is an angle A, and that fits very nicely in there. Mark off point C, and draw another quadrilateral, angle A. And then you can keep going in any direction. So right there we have a tiling using a general quadrilateral. Now, that is technically not the only kind of general quadrilateral. The previous, I'm not going to talk too much about this, but I do want to finish all quadrilaterals. So the previous quadrilateral is called a convex quadrilateral. And a tiling exists, a regular tiling, an edge-to-edge tiling, exists for any convex quadrilateral for the same reason over here. Now, what's convex quadrilateral? What does that actually mean? Well, it actually means if you connect any corners, it doesn't go outside of the quadrilateral. But I think it's best understood if we illustrate a non-convex quadrilateral. What about non-convex quadrilaterals? Well, what would that look like? It could look something like this. Where the angle's inside, that's a lousy drawing, I guess. Right here we have a non-convex quadrilateral, and the reason it's non-convex, if you connect these 2 points, then it leaves the quadrilateral. So a convex one is, all of the angles are like, bulging out, kind of. Well, maybe I shouldn't say that. That's not clear given this angle. But notice here, if we label the angles inside, how about this definition? And this non-convex one has an angle larger than 180 degrees. And this one, they're all less than 180 degrees. But in a non-convex quadrilateral, the angles do still add to 360. So I'll just say tilings exist by the same construction. The same construction meaning the same one over here where we piece together the angles. So this board right here tells us, what does it tell us? It tells us a tiling exists for any convex quadrilateral, a tiling exists for any non-convex quadrilaterals. So a tiling exists for any quadrilateral. Any four-dimensional figure, tilings exist. What about general five-gons? Well, we won't cover any of them, but I will tell you the book does discuss a couple of them. What about regular five-gons? So tilings using, general five-gons. There were a few discovered in the early 1900s, and then in the next, say, 60, 70 years, a few more were discovered. I think that it started with 4 classes of five-gons, so five-gons where the angles satisfy various conditions. And throughout time, 15 classes of general five-gons, 15 classes of five-gons can be used to tile. But it is not known if that is all there are. So at least 15 classes of five-gons tile the plane. What about general six-gons? Well, the question for six-gons and higher has been answered. General six-gons, and these are all in the textbook, there are exactly 3 classes of general sixgons that tile the plane. And what about general 7, I'll just say 7 plus gons, so 7 gons, 8 gons, and so on. I'll just tell you, there are none, and it has been shown that there are none. So the textbook does cover a few different other tilings, so in the PDF I would, well, I think it would be a good idea for you to look through pages 834 through 843. You don't really have to read anything unless you want to. 834 through 843 in the textbook. 834 to 843. Actually, that might be where the glare is. So 834 to 843. They go over some other tilings. They show the 3 classes of 6-gons, and they talk a little about the history of the general 5-gons. And there is an interesting blurb in there with, I believe it's 4 of these classes. Some lady just discovered them. She didn't have any formal math training. She was a housewife, and she just decided to play around with pentagons. And in doing that, she discovered classes, I believe, 10, 11, 12, and 13 of these 15. And that's worth reading. But in these, you'll see a few different other tilings that don't use necessarily shapes. They go through some Escher tilings, which are, some people may have seen things like that in art somewhere. Escher constructions show up. But these pages are definitely worth flipping through, at least looking at the pictures and seeing how some other tilings could look.